In this video we will see the move, load and store instructions. As seen before, we can use the Raspberry Pi 5 desktop. In case of headless, we connect with SSH, put the user and IP, enter the password and log in. Then we can list content. A third way is rpi-connect. As seen in the last video, we list the devices and have screen sharing and remote shell. We connect to terminal, wait for the process to end and maximize the window. Then we resize font and list content again. For better order, we create an ARM64 folder to have all programs together. We change folder and see that it is empty. We write the first example we made, placing global directive, start label, move immediate 5 to register X0 and exit. If we want GCC instead of as an LD, the first error is due to start label. GCC expects main. We use no start files. As we can see, executable file is built. We can use OBJ-DUMP to disassemble and see instructions in assembly language. By changing parameter to -, to see sections, we can observe several sections made by GCC, though not needed to execute. We are not even using advanced code, otherwise GCC generates extra code. Now we assemble and link manually with ASLD. We repeat OBJ-DUMP with S parameter, and we will see that only one section is shown with hex code of the 3 commands. To avoid writing AS and LD commands independently, plus execution line with echo, we can create a bash script header. Then we write the commands we want, for example, as to assemble LD to link and the execution line with echo at once. To run the script, we put bash command, then script name ASLD, then name without extension, we see execution and delete. In the second example, we use equal directive, which assigns constant value to a symbol. We set max to 100 for return. We execute script and see that the value printed by echo is 100. Note that label is replaced so no memory is used. To continue in order, we will rename tests to your1 test s. We list the files and only have the 2 examples and script. In the third example, we use alignment. Each instruction takes 32 bits, i.e. 4 bytes. Like word variables, we use nano. Now we declare a data section with data and create a variable named b that will contain 2 numbers plus instructions. We use script to assemble and link and see it returns 0, since we did not assign any value to return register X0. There will be cases where echo is not needed, nor deleting executable file. We copy ASLD to ASLD EC to have 2 scripts. We edit ASLD script, remove actual, and remove executable file parameter in rm command, so file stays for its analysis. We run it, see it printed nothing and left executable error 3 align. We use OBJ-DUMP S on it and see data and instructions. Later we will see stack. ARM64 requires 16-byte alignment. For this fourth example, we align data and code to 16 bytes. We copy example 04 aligns to 04 align 16. List content and edit program with nano. We add alignment to data and commands. We add data alignment with align 4 and code alignment with align 16. Both directives do exactly the same thing. Since align takes power of 2 exponent and align the amount of bytes we want to align, they match, save, and exit. We list content and run script with bash and U4 align 16 file. It did not print return value or delete executable. We inspect executable again with OBJ-DUMP and S parameter. As you notice now in data, there are 2 more values codes. Values in data are 0, but in instructions we see a hex code. We inspect with OBJ-DUMP and D added commands are NOPs. In example 5, we will use LDR instruction, which is a load register using an array. We declare it in data as A with 1, 2, and 3. We load address of global variable using LDR, x1 and equal sign and letter A. We see x1 as pointer to A. Then we load first position of array via LDR, register x0 and addressing via square brackets with x1 inside, then exit. We save, exit and execute ASLDEJ script with 05 LDR. Result gives us value 1, which is index 0 of array. This is direct addressing type, but there are 3 more with of state, immediate or register, pre-index and post-index. In example 6, we use the previous example copying to 06 LDR offset to show how addressing is done with the displacement. We will use normal offset, i.e. without modifying any register like in high-level addresses are like byte indices. We write MOV instruction, register x2 and immediate 8, representing an 8-byte offset from byte 0. We will take value 3. If they were indices, we would talk about index 2 of array, because arrays start with index 0 for 1 and index 1 for 2. We clear screen and then run script using ASLDEC and name 06LDR of FAT, which prints value 3, just as we mentioned. In example 7, we will use STR to save data in variables. We copy content of 05 LDR into 07 STR file. We use section for uninitialized data BSS, call it B, and use space with 8 byte size. We load the address of variable A. We load content of A, which is 10 to x2 via LDR, x2 and x1. We load address of B into x3. To store, we use STR instruction with register x2 and addressing to x3, meaning B equals A, and we return it as value. Run ASLDEC with parameter 07S3R. It prints 10, which is correct, because return value B equals A. We worked with numbers, but we can do it with characters, though low level uses ASCII. We copy content to 08 ARCS. Editing it with nano, we change a value to 0 and add a variable s of type string with word hola inside quotation marks. We load address of s into register x1. Once loaded, we access content. To get letter A, we need an offset of 3 bytes. Then we load address of A to x3 and save ASCII for letter A with STRB, then W2 and x3, and we return it. We run it and it prints 97, which is ASCII for a note use of register W2, same x2 but least significant half. In example 9, we copy content of 08 ARCS to 9 byte, because we will work with a smaller type. Then we edit with nano. We leave variable A defined as byte with 0, load address of A in x1, and load immediate 10 into x2. We use STRB instruction, which works like STR but with bytes, save value 10 in x1 address, which is variable A, and return. We run the script with 09 byte, and it prints 10. It's important that echo only prints values from 0 to 255. That is all for this video. If you liked it, subscribe, leave a like, and turn on notifications. See you in the next video.